So modern atomic theory. Atomic theory is the idea that all matter is composed of atoms. That's what we mean by atomic theory. And it grew out of observations and laws, specifically these three laws. The law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So we're going to talk about each of those. The law of conservation of mass states that in a chemical reaction, matter is neither created nor destroyed. And so this goes back to the experiments we talked about that Lavoisier did, burning things in closed containers. In a chemical reaction, the total mass of substances doesn't change. And atomic theory explains this. The particles, the atoms in those substances become rearranged when you have a chemical reaction, but they're not created or destroyed, they're just recombined. It's like taking a tower that you made out of Lego bricks, taking it apart and making two small houses out of it. You have the same number of each kind of Lego brick. If you weighed the bricks before and after, they're not going to change in their mass. You just put them together differently. That's what's happening in a chemical reaction, and that's a very important idea to understand. Here's an example. If we take sodium metal, it's shiny, it's soft enough that you can just cut it with a knife, and it's also highly reactive. If we take some sodium metal and react it with chlorine gas, it's got kind of a yellowish color and it's toxic, you don't want to be breathing that. And you put those two together, they will undergo a chemical reaction and form sodium chloride, which we call table salt. And while too much table salt isn't good for you, not enough will also kill you. So it's necessary for life. If we started with 7.7 grams of sodium, and this is what sodium might look like, individual sodium atoms all lined up neatly. And here's the chlorine, 11.9 grams of chlorine. Chlorine forms those little molecules, and because it's a gas, it's just bouncing around in this flask. When we combine these, they form a new substance. Now the red and the purple balls are arranged in an alternating pattern. Because the atoms are arranged differently, this substance has much different properties than the reactants that it came from. But the total mass of sodium chloride, here we go, total mass of sodium chloride formed is going to equal the mass of sodium that reacted and the mass of chlorine that reacted. Does that make sense? Law of conservation of mass. Definite proportions. French chemist Joseph Proust made some observations about compounds and what they're composed of. The law of definite proportions. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. Often the easiest way to study this is to take the compound and separate it into its elements. Water is something that's actually fairly easy to break down. You can just pass enough electric current through it and separate it into hydrogen and oxygen. So if you take 18 grams of water and decompose it, you'll get 16 grams of oxygen and 2 grams of hydrogen. So if we look at the ratio of masses, the ratio of the mass of oxygen to hydrogen is a ratio of 8 or 8 to 1. 8 mass units of oxygen for every 1 mass unit of hydrogen. And that will be true of any water that you decompose. So let's look at this example. 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon, and the other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. Well, we need to know what the law of definite proportions is. It tells us that the ratio of the masses should be the same for both samples. So we're given the mass of oxygen, the mass of carbon for the one sample, mass of oxygen for mass of carbon for the other sample. So what we need to do is show that the ratios are the same. So for sample 1, we've got 17.2 grams of oxygen to 12.9 grams of carbon. You could do the ratio the other way, carbon to oxygen, I prefer to deal with numbers that are greater than 1, and so I usually choose to put the larger number on top. So 17.2 divided by 12.9, 1.333333. How many significant figures should that result have? 3. So if I round that according to the rules for significant figures, I'm going to end up with 1.33. That's the ratio for sample 1. We're going to do a similar thing for sample 2. That one gave us 10.5 grams of oxygen and 7.88 grams of carbon. So I'm going to find the ratio of those two. 10.5 divided by 7.88. This one should also have 3 significant figures. So I'm going to write down my 3 sig figs, and then I'm going to throw in 2 or 3 extras and round it, and I'm going to come up with 1.33. The ratios are the same. Does this support the law of definite proportions? Yes, it does. Any questions? What I think students find difficult about problems like this on a worksheet or an exam is you've all had chemistry before and you've learned how to do much fancier things. And this isn't converting to moles or anything like that. It's just looking at ratios of masses. And so sometimes it's hard to take a step back and look at the simple explanation. So then the law of multiple proportions. Dalton again, 1804. Law of multiple proportions can be stated different ways, but this is the way your textbook explains it. When 2 elements, just call them A and B, when 2 elements form 2 different compounds, the masses of element B, that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. So an atom of A can combine with 1, 2, 3, or more atoms of B. You can't have A and half an atom of B, right? Or 2.5 atoms of B. It has to be whole numbers of atoms. Because of that, the masses of B that will react with a fixed amount of A are going to be related to each other as small whole numbers. So let's look at this, because that's a bit hard to understand. Let's look at carbon monoxide and carbon dioxide. They're both composed of carbon and oxygen. So the mass ratio of oxygen to carbon in carbon dioxide is 2.67 to 1, meaning 2.67 grams of oxygen are going to react with 1 gram of carbon. In carbon monoxide, the ratio is 1.33 to 1. We just did that calculation for 2 different samples. So 1.33 grams of oxygen will react with 1 gram of carbon. Law of multiple proportion says that these 2 ratios, this number and this number, are related in relationship of a small whole number. So here we have carbon dioxide, carbon monoxide. Here are their ratios. And so if we take the mass of oxygen that reacts with 1 gram of carbon in the carbon dioxide, 2.67, and the mass of oxygen that will react with the same amount of carbon in carbon monoxide, 1.33, we get a small whole number, 2. Carbon dioxide has twice as much oxygen as carbon monoxide. It has to be a small whole number, because if you have 1 carbon atom, you could have 1 oxygen atom, you could have 2 oxygen atoms, you could have 3 oxygen atoms, but you can't have anything in between. So the mass of oxygen must be twice or 3 times or 4 times as much. Does that make sense? Any questions? Here's an example of a problem on multiple proportions. Hydrogen and oxygen both form water and hydrogen peroxide. Hydrogen and oxygen form both water and hydrogen peroxide. Decomposition of a sample of water forms 0.125 grams of hydrogen for every 1 gram of oxygen. Decomposition of a sample of hydrogen peroxide forms 0.250 grams of hydrogen for every 1 gram of oxygen, show that these results are consistent with the law of multiple proportions. So we're given the amount of hydrogen that combines with 1 gram of oxygen for each of these compounds. Where's that other number? There it is. So what we want to do is we want to find the ratio of these. Put the bigger number on top, 0.250 grams to 0.125 grams. Notice the grams cancel out, the ratio doesn't have units, and that's going to give us a ratio of 2. If this came out to be a number that wasn't a whole number, like 2.5 or something, that would not support the law of multiple proportions. It would indicate that something was wrong somewhere. Any questions? Yes?
Does that happen? Like, something goes wrong?
Yeah, it could happen. Something goes wrong. Maybe you have a sample that isn't a pure sample. Maybe one of your samples is a mixture of hydrogen peroxide and water. So then when you decomposed it, you wouldn't get the correct ratio because you had a mixture of things. And I mean, there's really an infinite number of ways you could screw up getting the data. So we've talked about the idea of atomic theory. This was John Dalton's atomic theory. You don't need to know this verbatim, but you should know what the ideas are in Dalton's atomic theory. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. In chemical reactions, atoms only change the way they are bound together with other atoms. There are a couple of points in this theory that had to be modified later, but overall it's basically correct.